All right, this last thing I kind of want to pull some of this stuff together. So kind of link together planar graph goals along with how to Tori inform what we can do. For instance, if we fail to draw a graph as a planar graph, is there any methods to kind of work around that? All right, the answer is like no, we can't just force it to be planar, but we do have some information now about tools. So just for variety, I want to do K3-3. We've done K5 a whole bunch. Oops, so we're talking right at the same time. If we have time, or time and space one time, I'll do K5 like this as well. I probably will. All right, so you can definitely draw K3-3 on a torus. Let me just do that real quick as an exercise. But I want to show you another perspective on doing this that might be fun but also very useful. All right, you do not have to draw K3-3 to emphasize that it's bipartite, but it's generally my favorite way of doing it, so it's really clear that it's K3-3. Okay, I have to get all of these vertices connected to all of these vertices, and so this one's done. All right, now I have a lot of more connections to make, so this vertex needs to connect to this one and this one. To do that, I'm okay doing this, and I feel comfortable doing this. Okay, the reason I do is because this vertex here is done, and while it's not trapped yet, because I can get to it this way, I can be cautious about trapping it. Again, this one's also not trapped on here, but it's done as well. All right, so there's actually not a lot left to do. So this one needs to connect to that one, and this one needs to connect to that one. Okay, so actually you don't have to do much clever stuff here. Let me just go off the screen. Again, I'll use two colors, so hopefully you can follow that. And then this one connected to that one, so I'll go this way and get connected. Okay, so there's K3-3 on a torus. All right, and if you wanted to, as an exercise, maybe we should do it just for practice. We can analyze the faces. So let me go ahead and give them numbers with green. So this is face number 1, and it's this. Maybe here's face number 2. And as I might have suggested, there's actually only one other face. So let's just double check that that's the case. So I'll call this face number 3, and now let's just check to see if it is just one other face. All right, so let's take a lap. Go around the face. Take a tour of the face. Okay, go off here. Here we go. Oh, there we go. This is a long walk, right? Let's keep going around. Oh, still going. And still going. And there we go. Finally, we're back to where we started, right? It's always a surprise to me. I've been doing this for years. Okay, we have 3 faces. As opposed to counting its degree first and then verifying that's what we expect, let's see what we would expect its degree to be, and then just do a quick count to verify that that's the case. All right, face 1 here, let me indicate degree. Let me use orange, it's a little bit more visible. Face 1 has degree 3, right? It's a triangle. Double check that. Face 2 is also not a triangle. There are no odd degree faces in a bipartite graph. All right, we should know that. I should have known that. It's 4. It's a square. That's a 4. That's 4. Once that dries, I might be able to fix it in here in a second. Still not very dry. I'm getting there. Okay, 4. Cool. All right, let's see what this face number 3 degree would have to be. All right, we know that K3-3 has a certain number of edges, right? The sum of degrees, there's 6 vertices, all degree 3. It's 18, so it looks like E equals 9. Okay, but the 2e is really important, right? 2e is 18. All right, so 4 plus 4 plus x needs to be equal to 2e, which is 18. So it looks like x here would be 10. So face number 3, we suspect, and this better work, has degree 10. Right, it's a decagon. Alright, we can go through and double check it. So there's first one, second one, again this is continuing the second one, third, fourth continued, 5, 6, 7, because we're hitting the other side of that one, 7 continued, 8, 9, because we're on the other side, and 10. Okay, this takes practice to do, but hopefully these sort of steps and way of thinking can eventually sink in. Okay. Alright, so I haven't done anything new yet. This is just an exercise of stuff we've done last time. Let's take a look at another way of thinking about this. So one thing I've suggested is to think about a torus equals a sphere plus a handle. Right, so artistically speaking, topologically speaking, these two surfaces are homeomorphic to one another. Let me really emphasize the ridiculousness of my handle here. Okay. All right, in this handle, can make it kind of coffee cup shape-ish. Could look like that, right? The attachment points being further apart. You can make the attachment points closer together, that's what happened there. Or you can kind of move these wherever you want, right? It's still a sphere with a handle. So how about we try to draw a graph on a sphere, and then when we get stuck, we'll add a handle. Okay, let's do this with K33. So I'm not going to try to draw like a square because I don't want to suggest that I'm drawing on a torus. But what I can do is I can draw a really big sphere. Then I'm going to draw K33 on it. I just want it to be big enough so I don't have to think about it being a sphere too much, if that makes sense. Alright, and then when I get stuck, I'm going to add a handle to it. So I'm going to try to do roughly the same sort of thing I did last time, or with everything. You don't have to take this approach to drawing it. Let's see, I'm trying to mimic what I'm doing, so I'll go there. What was the other one I did? I went from here to here. Okay, now I can do another one without crossing edges. I can get, say, this one and this one connected, or I can get this one and this one connected, but I can't do them both. Let me show you. Let me just try to do one of them. So let me connect these two together. By doing that, I've trapped this one and it can no longer be connected to that one. Right, so I've kind of approached my failure point to draw this graph. All right, now, this is very, very important when it comes to this subject. Because I messed it up doesn't mean it's not planar. We know K33 is not planar for other reasons. We know it's not planar because it has too many edges. And so the handle is necessary. All right, just because you fail to draw a graph as a planar graph doesn't mean it's not planar. It either means one of two things. It could mean it's not planar, or it could mean you didn't do it right, right? You trapped a vertex too soon. All right, so that's not what I'm doing here. What I'm doing here is I'm saying, okay, let's think about this as a problem that we're trying to solve, and we came into an issue where we can't draw this thing on a sphere, but we're going to add a handle. Okay, so my handle, think of it right here, the attachment points are going to be these purplish circles. Okay, so my handle's attached there and there. All right, so think about it. There's the handle attachment. Right, so there's now a handle attached. And what I can do is now I can say, okay, y'all, I'm going to jump on the handle, go across the handle, and come off the bottom there. Ta-da! You got it like that. Alright, this idea is used in science fiction all the time. This is what you'd call a two-dimensional wormhole. Right? The idea is to use these in 3D if you're doing this with sort of space science fiction. You want to travel from one point in the universe to another. You would do a three-dimensional version. And a three-dimensional version, instead of having circular attachment points to the wormhole, you'd have spherical attachment points, right? And you would travel into a sphere to travel along the wormhole and then exit a sphere, right? These are circles, so it's got that. Now all you have to do is be able to visualize this in 4 dimensions to kind of see how all the attachment points go together, and that's really hard,